Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. The study of volcanic rocks, which are more formally referred to as extrusive igneous rocks, constitutes one of the most extensively documented and methodically categorized branches of geological science. And it is through the careful examination of these materials that a remarkably detailed understanding of the processes occurring deep within the interior of the Earth has been gradually assembled over the course of many decades of painstaking research. Volcanic rocks are, by definition, those igneous rocks that have formed as a result of the solidification of molten material, known as magma, upon reaching or very nearly reaching the surface of the Earth, and it is this particular characteristic, the cooling and crystallization of molten rock at or near the surface, that distinguishes them from their plutonic counterparts, which cool and solidify at considerable depths beneath the ground. The temperatures at which these processes occur are substantial, typically ranging from approximately 700 degrees Celsius at the lower end of the spectrum to as high as 1,300 degrees Celsius for the most fluid and least silica-rich compositions. And it is the interplay between temperature, pressure, and chemical composition that ultimately determines the nature of the rock that is produced. The formation of magma itself is a process that begins deep within the Earth's mantle, which is the thick layer of silicate rock that lies between the thin outer crust and the metallic core, extending from a depth of roughly 30 kilometers beneath the continents, or approximately 7 kilometers beneath the ocean floors, down to a depth of approximately 2,900 kilometers. It is within this vast region that the process known as partial melting occurs, a phenomenon in which only a fraction of the solid mantle rock is converted to a liquid state, while the remainder persists as a solid. This partial melting is not a simple or uniform process, and it can be triggered by several distinct mechanisms, including the reduction of pressure that occurs when mantle material rises toward the surface. As is the case at mid-ocean ridges and mantle plumes, the addition of volatile substances such as water, which has the effect of lowering the melting point of the rock, as is commonly observed in subduction zone environments, and the direct increase of temperature, which may result from the intrusion of hotter material from deeper within the mantle. The composition of the magma that is produced through partial melting is determined by a number of factors, including the composition of the source rock, the degree to which melting has occurred, the depth and pressure at which the melting takes place, and the presence or absence of volatile components such as water and carbon dioxide. One of the most fundamental parameters used to classify magmatic compositions, and by extension the volcanic rocks that are ultimately derived from them, is the silica content, which is expressed as the weight percentage of silicon dioxide, also written as SiO2. This single chemical parameter serves as the basis for a widely used classification system that divides igneous rocks into 4 broad categories, each of which is associated with a characteristic range of physical properties, mineral assemblages, and eruptive behaviors. The first of these categories is referred to as felsic, a term derived from the words feldspar and silica, and it encompasses those compositions in which the silica content exceeds 63% by weight. Felsic magmas and the rocks they produce are typically light in color, ranging from white to pale gray or pink, and they are characterized by the presence of minerals such as quartz, potassium feldspar, and sodium-rich plagioclase. The viscosity of felsic magmas is notably high, owing to the extensive polymerization of silica tetrahedra within the melt, and this high viscosity has significant implications for the manner in which felsic eruptions proceed, as the magma's resistance to flow tends to result in the buildup of pressure within volcanic conduits, leading to explosive eruptions of considerable violence. The temperature of felsic magmas is generally the lowest of the four categories, typically falling in the range of 700 to 850 degrees Celsius. The second category is described as intermediate, and it includes those compositions in which the silica content falls between 52 and 63% by weight. Intermediate magmas produce rocks that are medium in color, often appearing in various shades of gray, and they contain mineral assemblages that include plagioclase feldspar of intermediate composition, amphibole, and pyroxene. The viscosity of intermediate magmas falls, as one might anticipate, between the extremes exhibited by felsic and mafic compositions, and the eruptions associated with intermediate magmas can range from moderately explosive to effusive, depending on the specific conditions that prevail. Temperatures for intermediate magmas typically range from approximately 850 to 1050 degrees Celsius, which represents a measurable increase over the felsic range. The third category is known as mafic, a term that is derived from magnesium and ferric, referring to the iron-rich character of these compositions. Mafic magmas contain between 45 and 52% silica by weight, and they produce rocks that are characteristically dark in color, ranging from dark gray to black. The mineral assemblages found in mafic rocks include calcium-rich plagioclase, pyroxene, and olivine, and these minerals contribute to the relatively high density of mafic rocks compared to their felsic and intermediate counterparts. The viscosity of mafic magmas is comparatively low, a consequence of the reduced degree of silica polymerization within the melt, and this low viscosity allows mafic lavas to flow readily across the surface, sometimes traveling distances of many kilometers from the vent before solidifying. The temperatures of mafic magmas are correspondingly higher, generally falling in the range of 1050 to 1200 degrees Celsius. And it is this combination of high temperature and low viscosity that produces the characteristically fluid lava flows that are associated with basaltic volcanism. The fourth and final category in this classification scheme is referred to as ultramafic, and it encompasses those rare compositions in which the silica content falls below 45% by weight. Ultramafic magmas are exceptionally rich in magnesium and iron, and the rocks they produce, such as komatiite, are extremely dense and dark in color. These magmas are characterized by the lowest viscosities and the highest temperatures of any magmatic compositions, with temperatures that may exceed 1,300 degrees Celsius and, in the case of Archean komatiites, may have reached temperatures as high as 1,600 degrees Celsius. Ultramafic volcanic rocks are exceedingly rare in the modern geological record, and the vast majority of known examples date from the Archean, which ended approximately 2,500 million years ago. A circumstance that is generally attributed to the gradual cooling of the Earth's mantle over geological time. The relationship between silica content and viscosity is one of the most consequential in all of volcanology, as it exerts a controlling influence over virtually every aspect of volcanic behavior, from the style of eruption to the morphology of the volcanic edifice that is constructed over time. Silica, in its molecular form as silicon dioxide, consists of a silicon atom bonded to 4 oxygen atoms in a tetrahedral arrangement, and these tetrahedra have a pronounced tendency to link together through shared oxygen atoms, forming chains, sheets, and three-dimensional networks of considerable complexity. In silica-rich melts, these polymerized networks are extensive and interconnected, creating a structure that resists deformation and flow, much as a tangled mass of long-chain polymers would resist being poured from a container. In silica pore melts, by contrast, the network is less developed. The chains and clusters are smaller and less interconnected, and the melt consequently flows with much greater ease. The viscosity of a silica-rich rhyolitic magma, which typically contains approximately 72% SiO2, has been measured at values on the order of 10 to the power of 6 to 10 to the power of 9 pascalseconds at typical eruption temperatures, a range that is comparable to the viscosity of warm asphalt or thick tar. A basaltic magma, by contrast, with a silica content of approximately 49%, exhibits viscosities on the order of 10 to the power of 1 to 10 to the power of 3 pascalseconds, which is roughly comparable to the viscosity of honey or warm syrup. This difference of several orders of magnitude in viscosity has profound consequences for the behavior of volcanic systems, and it is largely responsible for the observation that basaltic volcanoes, such as those found in Hawaii and Iceland, tend to produce relatively gentle effusive eruptions characterized by flowing rivers of lava, while rhyolitic and dacitic volcanoes, such as Mount St. Helens and Mount Pinatubo, are prone to catastrophic explosive eruptions that can inject vast quantities of ash and gas into the atmosphere. The process of crystal formation during the cooling of magma is another topic of considerable importance to the understanding of volcanic rock types, and it is governed by the principles of thermodynamics and kinetics that describe the transformation of matter from a disordered liquid state to an ordered crystalline solid. As magma cools, whether at the surface or at depth, individual mineral phases begin to crystallize out of the melt at specific temperatures that are determined by the composition of the magma and the pressure under which it is cooling. The sequence in which minerals crystallize is not random, but follows a well-defined pattern that was first described in systematic detail by the Canadian petrologist Norman Levi Bowen in the early decades of the 20th century, and which has come to be known as Bowen's reaction series, a topic that will be discussed in greater detail in a subsequent portion of this discussion. When magma reaches the surface and is exposed to the atmosphere or to bodies of water, the rate of cooling increases dramatically compared to what would be experienced at depth within the Earth's crust. This rapid cooling has the effect of limiting the time available for crystal growth, with the result that the crystals that form in volcanic rocks are typically very small, often too small to be seen with the unaided eye. A textural characteristic that is described by the term aphanitic. In some cases, the cooling is so rapid that crystals have no opportunity to form at all, and the melt solidifies as a glass, which is an amorphous solid lacking any long-range crystalline order. Obsidian is the most well-known example of a volcanic glass, and its smooth, conchoidal fracture surfaces and vitreous luster are a direct consequence of its glassy, non-crystalline structure. In contrast to volcanic rocks, plutonic rocks, which are also referred to as intrusive igneous rocks, form when magma solidifies at considerable depths beneath the Earth's surface, where it is insulated by the surrounding rock and cools at a much slower rate. This slow cooling allows ample time for the growth of large, well-formed crystals, and the resulting rocks exhibit a coarse-grained texture, known as phaneritic, in which individual mineral crystals are readily visible to the naked eye. Granite, which is the plutonic equivalent of rhyolite, is perhaps the most familiar example of a phaneritic rock, and its characteristic speckled appearance, with clearly visible grains of quartz, feldspar, and mica, stands in marked contrast to the fine-grained or glassy texture of its volcanic counterpart. The distinction between volcanic and plutonic rocks is not merely one of texture, but also reflects fundamental differences in the geological environments in which they form and the rates at which the processes of cooling and crystallization proceed. A plutonic rock such as granite may have cooled over a period of thousands to millions of years, during which time the crystals grew slowly and had the opportunity to develop well-defined geometric forms and to segregate into distinct mineral domains. A volcanic rock such as rhyolite, by contrast, may have cooled in a matter of hours to days, or in some extreme cases, seconds, and the resulting texture preserves a record of this rapid cooling in the form of microscopic or absent crystals, flow banding, and other features that are unique to rocks formed at the surface. It is also worth noting that there exist intermediate cases in which magma begins to cool slowly at depth, allowing some large crystals to form, and then is subsequently erupted at the surface, where the remaining liquid portion cools rapidly. The result is a rock with a mixed texture known as porphyritic, in which large crystals, called phenocrysts, are set in a fine-grained or glassy matrix, called the groundmass. Porphyritic textures are extremely common in volcanic rocks and provide valuable information about the thermal history of the magma, as the size and composition of the phenocrysts can be used to infer the conditions that prevailed during the initial slow cooling phase, while the ground mass records the conditions of the final rapid cooling at the surface. The study of volcanic rocks thus encompasses a broad range of topics, from the deep-seated processes of magma generation in the mantle to the surface phenomena of eruption and solidification. And it is through the integration of these various lines of evidence that geologists have been able to construct a comprehensive understanding of the nature and origin of these materials. The classification of volcanic rocks by their silica content, while seemingly simple, reflects fundamental differences in the conditions under which the magma was generated, the source materials from which it was derived, and the tectonic setting in which the volcanic activity occurred. Felsic rocks are most commonly associated with convergent plate boundaries and continental settings, where the recycling of crustal material through subduction and the differentiation of magma through fractional crystallization tend to produce silica-rich compositions. Mafic rocks, on the other hand, are most commonly found at mid-ocean ridges and oceanic hotspots, where the partial melting of the upper mantle produces magma of basaltic composition with relatively low silica content. The temperature at which a particular magma will begin to crystallize, known as the liquidus temperature, and the temperature at which crystallization is complete, known as the solidus temperature, are both functions of the magma's composition and the pressure under which it is cooling. For a typical basaltic magma at atmospheric pressure, the liquidus temperature is approximately 1,200 degrees Celsius and the solidus temperature is approximately 1,000 degrees Celsius, giving a crystallization interval of roughly 200 degrees. For a rhyolitic magma under similar conditions, the liquidus temperature is approximately 900 degrees Celsius and the solidus temperature is approximately 700 degrees Celsius, again yielding a crystallization interval of about 200 degrees, but at a significantly lower absolute temperature. These temperature ranges have been determined through extensive experimental studies conducted in laboratory settings, in which synthetic magmas of known composition are heated to temperatures above their liquidus, and then cooled at controlled rates, while the onset and progress of crystallization are monitored through various analytical techniques. The density of volcanic rocks is another physical property that varies systematically with composition and is of practical significance in a number of geological and engineering contexts. Felsic volcanic rocks, such as rhyolite, typically have densities in the range of 2.4 to 2.6 grams per cubic centimeter, reflecting the predominance of relatively light minerals such as quartz and alkali feldspar. Mafic volcanic rocks, such as basalt, are denser, with typical values ranging from 2.8 to 3.0 grams per cubic centimeter, owing to the presence of iron and magnesium-rich minerals such as pyroxene and olivine. These density differences, while seemingly modest in absolute terms, have important implications for the buoyancy-driven processes that control the ascent of magma through the crust, as well as for the isostatic balance of crustal blocks, which is the principle that governs the elevation of the Earth's surface relative to the underlying mantle. The porosity of volcanic rocks, which is a measure of the proportion of void space within the rock, is highly variable and depends on the conditions under which the rock cooled and solidified. Dense, slowly cooled lava flows may have very low porosity, on the order of a few %, while rapidly cooled, gas-rich eruption products such as pumice may have porosities exceeding 80%. The vesicles, or gas bubbles, that are responsible for this porosity form as dissolved volatile components, principally water and carbon dioxide, come out of solution as the magma depressurizes during its ascent to the surface. The size, shape, and distribution of vesicles within a volcanic rock preserve a record of the degassing process and can be used to infer information about the volatile content of the original magma, the rate at which it ascended, and the pressure conditions that prevailed at the time of solidification. The magnetic properties of volcanic rocks are also of considerable scientific interest, as many volcanic minerals, particularly magnetite and certain iron-bearing silicates, are capable of recording the orientation and intensity of the Earth's magnetic field at the time the rock cooled below a critical temperature known as the Curie point, which is approximately 580 degrees Celsius for magnetite. This phenomenon, known as thermoremnant magnetization, has been instrumental in the development of the theory of plate tectonics, as the systematic study of magnetic anomalies preserved in the volcanic rocks of the ocean floor provided some of the most compelling evidence for the process of seafloor spreading. The alternating pattern of normal and reversed magnetic polarity recorded in the basaltic rocks on either side of mid-ocean ridges was first identified in the early 1960s and was recognized as being consistent with the hypothesis that new oceanic crust is continuously being created at the ridges and spreading outward in both directions, carrying with it a frozen record of the periodic reversals of the Earth's magnetic field. The thermal conductivity of volcanic rocks, which is a measure of their ability to conduct heat, is another physical property that varies with composition, porosity, and degree of crystallinity. And it has important implications for the rate at which lava flows cool and solidify after eruption. Dense, non-vesicular basalt has a thermal conductivity of approximately 1.5 to 2.5 watts per meter per Kelvin, while highly vesicular varieties, in which the air-filled pores act as thermal insulators, may have conductivities as low as 0.5 watts per meter per Kelvin. Felsic volcanic rocks generally have somewhat lower thermal conductivities than their mafic counterparts, reflecting their lower density and the presence of quartz, which, while itself a good thermal conductor in its crystalline form, contributes to a more silica-rich glass in volcanic settings that tends to have lower conductivity. These values of thermal conductivity, combined with the specific heat capacity of the rock, which is typically in the range of 800 to 1,200 joules per kilogram per Kelvin for most volcanic rock types, determine the rate at which a cooling lava flow loses heat to its surroundings, and they can be used in thermal modeling studies to predict the time required for a lava flow of a given thickness to solidify completely. The mechanical properties of volcanic rocks, including their compressive strength, tensile strength, and elastic modulus, are of considerable practical importance in engineering applications, as these properties determine the suitability of the rock for use as a construction material and its behavior under the loads and stresses that are encountered in buildings, roads, and other infrastructure. The compressive strength of dense, non-vesicular basalt is typically in the range of 100 to 300 megapascals, making it one of the stronger common rock types and suitable for use in demanding applications such as road surfacing and railroad ballast. Rhyolite and other felsic volcanic rocks tend to have somewhat lower compressive strengths, typically in the range of 50 to 200 megapascals, while highly vesicular rocks such as pumice and scoria have much lower strengths, often less than 10 megapascals, reflecting the weakening effect of the numerous pores and voids within the rock. The weathering behavior of volcanic rocks at the Earth's surface is governed by a complex interplay of physical, chemical, and biological processes that gradually break down the rock and convert it into soil and dissolved chemical species. Physical weathering processes, including frost wedging, in which water freezes and expands within cracks in the rock, thermal expansion and contraction resulting from daily and seasonal temperature variations, and the mechanical action of plant roots growing into fractures, serve to break the rock into progressively smaller fragments without changing its chemical composition. Chemical weathering processes, which are the dominant mechanism of rock breakdown in warm, humid climates, involve the reaction of minerals in the rock with water, dissolved carbon dioxide, and organic acids, resulting in the dissolution of some mineral components and the transformation of others into clay minerals and iron oxides. The rate of chemical weathering is strongly influenced by the mineral composition of the rock, with olivine and volcanic glass being among the most rapidly weathered materials, and quartz being among the most resistant. The role of volcanic rocks in the global geochemical cycles of various elements is a topic of fundamental importance in Earth system science, as the weathering of volcanic rocks at the surface and the degassing of volcanic gases at eruption sites represent major fluxes of chemical species between the solid Earth and the atmosphere, hydrosphere, and biosphere. The weathering of basalt, in particular, has been identified as a significant sink for atmospheric carbon dioxide, as the dissolution of calcium and magnesium-bearing silicate minerals in basalt consumes CO2 through a series of chemical reactions that can be summarized as the conversion of silicate minerals plus carbonic acid into dissolved cations, bicarbonate ions, and silicic acid. It has been estimated that the global weathering of basalt consumes approximately 30 to 35% of the total CO2 consumed by silicate weathering on the continents. Despite basalt covering only approximately 5% of the continental land surface, a disproportionate contribution that reflects the relatively rapid weathering rates of the minerals found in basaltic rocks. In summary, the study of volcanic rocks begins with an understanding of the fundamental processes by which magma is generated within the Earth's mantle through partial melting, rises toward the surface driven by buoyancy forces, and solidifies upon reaching the surface to form the diverse array of rock types that are observed in the geological record. The classification of these rocks by their silica content into felsic, intermediate, mafic, and ultramafic categories provides a framework for understanding the relationships between chemical composition, physical properties, mineral assemblages, and volcanic behavior. The distinction between volcanic and plutonic rocks, which is fundamentally one of cooling rate and the resulting texture, reflects the different geological environments in which these two broad classes of igneous rock form and the study of textures. From aphanitic to porphyritic to glassy, provides insights into the thermal histories of individual volcanic rocks. These foundational concepts serve as the basis for the more detailed examination of specific volcanic rock types and their characteristics that follows. Basalt is, by a very considerable margin, the most abundant volcanic rock type found on the surface of the Earth, and indeed it is the most common rock type on the surfaces of the terrestrial planets as a whole, accounting for the vast majority of the ocean floor and forming extensive provinces on every continent. It is a fine-grained, dark-colored mafic volcanic rock with a silica content that typically falls in the range of approximately 45 to 52% by weight, with the most commonly cited average value being approximately 49% SiO2. The mineralogy of basalt is dominated by calcium-rich plagioclase feldspar, which typically comprises between 40 and 60% of the rock by volume, together with clinopyroxene, most commonly augite, which accounts for approximately 20 to 40%, and olivine, a magnesium iron silicate that is present in variable but often significant proportions, particularly in more primitive compositions. Minor minerals that may be present in basalt include orthopyroxene, magnetite, ilmenite, and, in some cases, small amounts of volcanic glass in the ground mass. The density of basalt in its fresh, unweathered state typically ranges from 2.8 to 3.0 grams per cubic centimeter, although vesicular varieties may have significantly lower bulk densities due to the presence of gas bubbles. The color of fresh basalt ranges from dark gray to black, and its fine-grained texture, a consequence of rapid cooling at or near the Earth's surface, means that individual mineral grains are generally not visible to the unaided eye. Under the polarizing microscope, however, thin sections of basalt reveal a rich assemblage of small, interlocking crystals, often displaying the characteristic intergranular or ophidic textures in which pyroxene crystals partially or completely enclose smaller laths of plagioclase. Basalt is produced by the partial melting of the upper mantle, specifically of a rock type known as peridotite, which is an ultramafic rock composed predominantly of olivine and pyroxene. The degree of partial melting required to produce a basaltic liquid from a peridotite source is typically in the range of 10 to 30%, with the exact composition of the resulting melt depending on the temperature, pressure, and volatile content of the source region. At mid-ocean ridges, where the upwelling of mantle material leads to decompression melting at relatively shallow depths of approximately 30 to 60 kilometers, the basalt that is produced is known as mid-ocean ridge basalt, or MORB. and it is characterized by a relatively depleted trace element signature, reflecting the fact that the mantle source has been previously depleted by earlier episodes of melt extraction. At oceanic hotspots, such as Hawaii, the basalt is produced by melting at somewhat greater depths, often in excess of 100 kilometers, and it is typically enriched in incompatible trace elements compared to MRB. A characteristic that is attributed to the involvement of deeper, less depleted mantle material, possibly including material from the lower mantle or even the core mantle boundary. The eruption temperature of basaltic lava is typically in the range of 1,100 to 1,250 degrees Celsius, and at these temperatures the lava has a relatively low viscosity, on the order of 100 to 1,000 pascal seconds, which allows it to flow readily across the surface and to form extensive sheet flows and lava tubes. The surface morphology of basaltic lava flows is classified into two principal types, known by their Hawaiian names: Pahoehoe, which has a smooth, ropey, or billowy surface texture and is produced by relatively slow-moving, fluid lava, and AA, which has a rough, jagged, clinker-like surface and is produced by lava that has partially cooled and lost some of its fluidity during flow. The transition from Pahoehoe to AA is driven primarily by increases in viscosity resulting from cooling, degassing, and crystallization, and it is an irreversible process under normal conditions. Andesite is the second major volcanic rock type in the classification scheme arranged by increasing silica content, and it derives its name from the Andes mountain range of South America, where rocks of this composition are particularly abundant. The naming convention was established by the German geologist Leopold von Buch in the early 19th century, who recognized the distinctive character of the volcanic rocks erupted by the numerous stratovolcanoes that line the western margin of South America. Andesite is classified as an intermediate volcanic rock, with a silica content that typically falls in the range of 52 to 63% by weight, with the most commonly cited average value being approximately 57% SiO2. This intermediate silica content places andesite between basalt and the more silica-rich dacite and rhyolite in terms of chemical composition, and it is reflected in the physical properties and mineralogy of the rock. The mineral assemblage of andesite characteristically includes plagioclase feldspar of intermediate composition, typically andesine or labradorite with a northite contents in the range of 30 to 50%, together with one or more ferromagnesian minerals such as amphibole, commonly hornblende, pyroxene, either orthopyroxene or clinopyroxene or both, and occasionally biotite. The color of andesite is typically medium gray to dark gray, and its texture is usually fine-grained or porphyritic, with phenocrysts of plagioclase and ferromagnesian minerals set in a fine-grained ground mass. The density of andesite ranges from approximately 2.5 to 2.8 grams per cubic centimeter, which is intermediate between the densities of basalt and rhyolite, consistent with its intermediate composition. Andesite is the characteristic volcanic rock of subduction zone environments, where oceanic lithosphere descends beneath either continental or oceanic lithosphere, and the complex processes of dehydration, melting, and magma mixing that occur in the overlying mantle wedge and crust produce magmas of intermediate composition. The volcanic arcs that are found at convergent plate boundaries around the Pacific Rim, including the Andes, the Cascades, the Aleutians, the Japanese islands, and the Indonesian archipelago, are all characterized by the eruption of large volumes of andesitic material. The eruption style of andesitic volcanoes is typically more explosive than that of basaltic volcanoes, owing to the higher viscosity and greater volatile content of andesitic magma, and the resulting volcanic landforms are commonly stratovolcanoes, also known as composite volcanoes, which are steep-sided, conical structures build up from alternating layers of lava flows and pyroclastic deposits. The eruption temperature of andesitic lava is typically in the range of 900 to 1,100 degrees Celsius, and its viscosity, while higher than that of basalt, is generally in the range of 10 to the power of 3 to 10 to the power of 5 pascalseconds at eruption temperatures. This moderate viscosity means that andesitic lava flows, while not as fluid or extensive as basaltic flows, can still travel significant distances from the vent under favorable conditions, although they tend to be thicker and more restricted in their lateral extent. Dacite is the next major volcanic rock type in the sequence of increasing silica content, and it is classified as a felsic volcanic rock with a silica content that typically falls in the range of 63 to 68% by weight, with the most commonly cited average being approximately 65% SiO2. The name dacite was proposed by the Austrian geologist Guido Stach in 1863, and it is derived from the Roman province of Dacia, which corresponds approximately to the territory of modern Romania, where rocks of this composition were first described in systematic detail. The mineral assemblage of dacite characteristically includes plagioclase feldspar, usually of intermediate to sodic composition, together with quartz, which appears as a significant phase for the first time in the sequence of increasing silica content, and one or more ferromagnesian minerals such as biotite, hornblende, or pyroxene. Small amounts of potassium feldspar may also be present, and accessory minerals commonly include magnetite, ilmenite, apatite, and zircon. The texture of dacite is frequently porphyritic, with prominent phenocrysts of plagioclase and quartz, and sometimes hornblende or biotite, set in a fine-grained ground mass that may range from light gray to medium gray in color. The density of dacite typically falls in the range of 2.5 to 2.7 grams per cubic centimeter, and its eruption temperature is generally between 850 and 1,000 degrees Celsius. The viscosity of dacitic magma is higher than that of andesite, typically falling in the range of 10 to the power of 5 to 10 to the power of 7 pascalseconds. And this increased viscosity contributes to the tendency of dacitic eruptions to be explosive in character, producing large volumes of pyroclastic material including ash, pumice, and ignimbrite. Dacite is commonly associated with the eruptions of large stratovolcanoes and caldera-forming systems at convergent plate boundaries. The 1980 eruption of Mount St. Helens in Washington state, United States, which produced a devastating lateral blast and pyroclastic flows that caused approximately 57 fatalities and billions of dollars in damage, involved the eruption of dacitic magma. Similarly, the 1991 eruption of Mount Pinatubo in the Philippines, which was one of the largest volcanic eruptions of the 20th century and injected approximately 20 million tons of sulfur dioxide into the stratosphere, causing measurable global cooling of approximately 0.5 degrees Celsius over the following 2 years, also involved magma of dacitic composition. Rhyolite represents the most silica-rich end member of the common volcanic rock types, with a silica content that typically exceeds 68% and may reach values as high as 77% by weight, with the most commonly cited average being approximately 72% SiO2. The name rhyolite was coined by the German geologist Ferdinand von Richthofen in 1860, and it is derived from the Greek word ryax, meaning stream of lava. A somewhat ironic etymology, given that rhyolitic lavas are among the most viscous and least likely to flow freely of all volcanic materials. The mineral assemblage of rhyolite is dominated by alkali feldspar, typically sonidine or orthoclase, and quartz, together with minor amounts of plagioclase, biotite, and occasionally amphibole or pyroxene. The ground mass of rhyolite is often partly or entirely glassy, reflecting the difficulty with which nucleation and crystal growth proceed in highly viscous, silica-rich melts. The color of rhyolite is typically light, ranging from white to pale gray, pink, or light brown, and its texture may be aphanitic, porphyritic, or glassy, with flow banding being a common feature. Flow banding consists of alternating layers of slightly different composition or degree of crystallinity, and it is produced by the laminar flow of highly viscous magma as it moves through the volcanic conduit and onto the surface. The density of rhyolite is generally the lowest of the major volcanic rock types, typically falling in the range of 2.4 to 2.6 grams per cubic centimeter, and its eruption temperature is the lowest as well, usually between 700 and 900 degrees Celsius. The viscosity of rhyolitic magma is extremely high, typically in the range of 10 to the power of 6 to 10 to the power of 9 Pascal seconds. And it is this extreme viscosity that is responsible for the characteristically explosive nature of rhyolitic eruptions. When rhyolitic magma is erupted effusively, which occurs relatively infrequently, it tends to form thick, stubby lava flows known as coulees, or dome-like structures known as lava domes, which grow by the slow extrusion of viscous magma from the vent. These domes may take years or even decades to grow to their full size, and they are prone to periodic collapse, which can generate pyroclastic flows known as block and ash flows. Far more commonly, however, rhyolitic eruptions are explosively violent, producing enormous volumes of pyroclastic material that may be deposited over areas of thousands of square kilometers. The largest rhyolitic eruptions, known as supereruptions, have produced individual deposits with volumes exceeding 1,000 cubic kilometers, and these events, while extremely rare, occurring on average perhaps once every 50,000 to 100,000 years, represent some of the most catastrophic natural phenomena to have occurred in Earth's history. Obsidian is a distinctive volcanic rock that is classified as a volcanic glass, meaning that it lacks the crystalline structure that characterizes most other rock types. It is formed when silica-rich magma, typically of rhyolitic or dacitic composition, is cooled so rapidly that the atoms within the melt do not have sufficient time to arrange themselves into the ordered, repeating patterns that constitute a crystalline lattice. The result is an amorphous solid, a material that possesses the rigidity and brittleness of a crystalline solid, but lacks any long-range structural order. Obsidian is typically black in color, although brown, gray, and even multicolored varieties are known, and it is characterized by a vitreous or glassy luster and a conchoidal fracture pattern, meaning that it breaks with smooth, curved surfaces that resemble the interior of a shell. The silica content of obsidian is typically in the range of 70 to 77% by weight, essentially identical to that of rhyolite, and the distinction between the two rock types is based entirely on texture rather than composition. The density of obsidian is approximately 2.35 to 2.60 grams per cubic centimeter, and its hardness on the Mohs scale is approximately 5 to 5.5, which is comparable to that of window glass. Obsidian has been valued by human cultures for thousands of years as a material for the manufacture of tools and weapons, as the conchoidal fracture produces exceptionally sharp edges that can be thinner than the finest surgical steel. Archaeological evidence indicates that obsidian tools were being manufactured and traded over distances of hundreds of kilometers as early as 700,000 years ago, and the geochemical fingerprinting of obsidian artifacts has become an important tool in archaeological research for reconstructing ancient trade networks. Pumice is another highly distinctive volcanic rock type, and it is remarkable primarily for its extremely low density, which in many cases is less than 1.0 grams per cubic centimeter, making it one of the very few rock types that is capable of floating on water. This low density is a consequence of the extremely high porosity of pumice, which typically ranges from 60 to 90% by volume, consisting of a vast number of thin-walled vesicles, or gas bubbles, that were formed during the violent degassing of volatile-rich magma during explosive eruption. The composition of pumice is most commonly felsic, typically rhyolitic or dacitic, although intermediate and even basaltic pumice, sometimes referred to as reticulite, has been documented. The color of pumice ranges from white to light gray for felsic compositions, and the texture is characteristically frothy and lightweight, with a rough, abrasive surface. Pumice is produced during explosive volcanic eruptions, particularly during the Plinian eruption columns that are associated with the most violent volcanic events. During such eruptions, The rapid decompression of volatile-rich magma as it rises through the volcanic conduit causes dissolved gases, principally water and carbon dioxide, to exsolve and form bubbles at an extremely rapid rate, fragmenting the magma into a froth of incandescent glass and expanding gas. This frothy material is ejected into the atmosphere, where it cools rapidly and solidifies, preserving the vesicular texture as a permanent feature of the rock. Deposits of pumice can be found at great distances from the source volcano, as pumice clasts are light enough to be carried by wind over distances of hundreds or even thousands of kilometers, and sufficiently buoyant to float on ocean currents for months or years. Scoria is, in many respects, the mafic equivalent of pumice, being a highly vesicular volcanic rock of basaltic or basaltic andesitic composition. It is distinguished from pumice by its darker color, which is typically dark brown, dark gray, or black, by its higher density, which, while still low compared to non-vesicular rocks, generally exceeds 1.0 grams per cubic centimeter, and thus prevents it from floating on water, and by the larger and more irregular shape of its vesicles. Scoria is produced during mildly to moderately explosive eruptions of mafic magma, particularly during Strombolian-type eruptions, in which blobs of incandescent lava are ejected to heights of tens to hundreds of meters above the vent by the bursting of large gas bubbles at the surface of the magma column. The accumulation of scoria around the vent builds up the steep-sided, conical landforms known as cinder cones or scoria cones, which are among the most common volcanic landforms on Earth, with tens of thousands of examples documented worldwide. The porosity of scoria typically ranges from 40 to 70%, and the vesicles are generally larger and more irregular in shape than those found in pumice, reflecting the lower viscosity and lower gas content of the mafic magma from which it is derived. The walls of the vesicles in scoria are often thicker than those in pumice, and the glass that comprises these walls is typically darker and more iron-rich, consistent with the basaltic composition of the rock. Scoria is widely used as a lightweight aggregate in construction, as a drainage material in landscaping and horticulture, and as a raw material for the production of cinder blocks. Tuff is a general term that is applied to any rock that is composed predominantly of volcanic ash and other pyroclastic material that has been consolidated, either through compaction, cementation, or welding. The grain size of the constituent particles may range from fine ash, with individual fragments less than 2 millimeters in diameter, to lapilli, with fragments ranging from 2 to 64 millimeters, and even blocks and bombs exceeding 64 millimeters in some cases. The composition of tuff is highly variable, as it depends on the composition of the magma from which the pyroclastic material was derived, and tuffs of basaltic, andesitic, dacitic, and rhyolitic composition are all well documented. The color of tuff similarly varies with composition, ranging from dark gray or brown for mafic varieties to light gray, pink, or white for felsic varieties. Ignimbrite is a specific type of tuff that is formed by the deposition and welding of pyroclastic flow deposits, which are dense, fast-moving currents of hot gas and pyroclastic material that cascade down the flanks of volcanoes during explosive eruptions. The temperatures within pyroclastic flows can exceed 700 degrees Celsius, and the weight of the overlying material compresses the lower portions of the deposit, causing the still hot and plastic glass shards and pumice fragments to flatten and weld together, producing a dense, hard rock with a distinctive texture known as eutaxitic texture. This texture is characterized by the presence of flattened, lens-shaped features called phaeum, which are the remnants of pumice clasts that have been compressed and deformed by the weight and heat of the overlying material. Well-welded ignimbrites can be nearly as dense and strong as lava flows, and they have been used as building stone in many parts of the world, including the famous pink ignimbrite that was used to construct many of the colonial-era buildings in the city of Arequipa, Peru. The volume of material produced during ignimbrite-forming eruptions can be staggeringly large. The Bishop Tuff of Eastern California, which was erupted from the Long Valley caldera approximately 760,000 years ago, has an estimated volume of approximately 600 cubic kilometers, and the Fish Canyon Tuff of southwestern Colorado, which was erupted approximately 28 million years ago, is one of the largest known ignimbrites, with an estimated volume of approximately 5,000 cubic kilometers. These enormous volumes of pyroclastic material are typically associated with the formation of calderas, which are large, roughly circular depressions that form when the roof of a depleted magma chamber collapses following a massive eruption. The textures of volcanic rocks are among the most informative features available to the petrologist, as they preserve a detailed record of the physical conditions that prevailed during the cooling and solidification of the magma from which the rock was formed. The term texture, in the context of igneous petrology, refers to the size, shape, and arrangement of the mineral grains and glass that comprise the rock. And it is through the careful examination and classification of these textural features that a great deal of information about the cooling history, volatile content, and eruptive style of a volcanic rock can be deduced. Several principal textural types are recognized in volcanic rocks, each of which is associated with a specific set of formation conditions, and these will be described in turn. The aphanitic texture, which is also referred to as fine-grained texture, is the most common textural type found in volcanic rocks, and it is characterized by mineral crystals that are too small to be individually distinguished by the unaided eye, typically having dimensions of less than approximately 1 millimeter. This fine grain size is a direct consequence of the rapid cooling that occurs when magma reaches the Earth's surface, as the limited time available for crystal nucleation and growth results in the formation of a large number of very small crystals rather than a smaller number of larger ones. The rate of cooling at the surface of a lava flow can be extremely rapid, with temperatures dropping by hundreds of degrees within minutes to hours, and even the interiors of thick lava flows, which cool more slowly due to the insulating effect of the solidified crust, typically reach ambient temperatures within periods of months to years, which is still very rapid by geological standards. Under the polarizing microscope, aphanitic volcanic rocks reveal a dense mosaic of small, interlocking crystals, and the identification of the individual mineral phases requires the use of optical properties such as birefringence, extinction angle, and interference color. The porphyritic texture is another extremely common textural type in volcanic rocks, and it is characterized by the presence of two distinct populations of crystals of markedly different sizes within the same rock. The larger crystals, known as phenocrysts, typically range in size from a few millimeters to several centimeters, and they are set within a fine-grained or glassy matrix known as the ground mass. The phenocrysts represent crystals that grew during a period of relatively slow cooling, typically at depth within the Earth's crust, before the magma was erupted at the surface, while the ground mass represents the portion of the melt that solidified rapidly upon eruption. The contrast in crystal size between the phenocrysts and the ground mass thus records a two-stage cooling history, with an initial period of slow cooling followed by a sudden transition to rapid cooling at the time of eruption. The mineral species that form as phenocrysts in volcanic rocks are determined by the composition of the magma and the temperature and pressure conditions that prevailed during the slow cooling phase. In basaltic rocks, the most common phenocryst minerals are olivine, clinopyroxene, and calcium-rich plagioclase. In andesitic rocks, plagioclase, hornblende, and pyroxene are the typical phenocryst phases. In dacitic and rhyolitic rocks, plagioclase, quartz, biotite, and hornblende are commonly observed as phenocrysts. The size and abundance of phenocrysts provide information about the duration of the slow cooling phase and the degree of crystallization that had occurred before eruption. And it is not uncommon for phenocrysts to comprise anywhere from a few percent to as much as 50% of the volume of a porphyritic volcanic rock. The vesicular texture is produced by the presence of vesicles, which are holes or cavities within the rock that were formed by the expansion of gas bubbles in the magma during eruption. As magma rises toward the surface, the decreasing pressure causes dissolved volatile components, principally water and carbon dioxide, to exhale from the melt and form bubbles. Much as the dissolved carbon dioxide in a bottle of carbonated water forms bubbles when the cap is removed. If the magma solidifies while these bubbles are still present, they are preserved as vesicles in the resulting rock. The size, shape, and abundance of vesicles are highly variable, ranging from rocks with only a few small, scattered vesicles to the extreme case of pumice, in which vesicles may comprise 90% or more of the total volume. Vesicles in basaltic rocks tend to be relatively large and spherical, reflecting the low viscosity of the melt, while vesicles in more silica-rich rocks tend to be smaller and more elongated or irregular, reflecting the higher viscosity that impedes the free expansion and coalescence of gas bubbles. The glassy texture, as its name suggests, is characterized by the absence of any crystalline structure, the rock instead consisting entirely of volcanic glass, which is an amorphous solid. This texture is produced when the cooling of the magma is so rapid that the atoms within the melt have insufficient time to migrate into the ordered arrangements that constitute crystal lattices. Glassy textures are most commonly developed in silica-rich compositions, such as rhyolite and dacite, because the high viscosity of these melts impedes the diffusion of atoms that is necessary for crystal nucleation and growth, making it more likely that the melt will solidify as a glass even at moderate cooling rates. In mafic compositions, by contrast, the lower viscosity and more fluid nature of the melt facilitate rapid crystal nucleation, and truly glassy textures are relatively uncommon, being restricted to situations of extremely rapid cooling, such as the outermost surfaces of pillow lavas erupted on the deep ocean floor, where the lava comes into contact with near-freezing seawater. The pyroclastic texture is found in rocks that are composed of fragments of volcanic material that were ejected during explosive eruptions and subsequently deposited and consolidated. The fragments, collectively known as tephra or pyroclasts, may include angular shards of volcanic glass, broken crystals, and pieces of pre-existing rock that were shattered by the force of the eruption. The size of the pyroclasts ranges from fine ash, with individual particles less than 2 millimeters in diameter, to lapilli, which range from 2 to 64 millimeters, to blocks and bombs, which exceed 64 millimeters. The degree of consolidation of pyroclastic deposits varies considerably, from loose, unconsolidated ash deposits to densely welded ignimbrites, in which the individual glass shards have been fused together by heat and compaction into a hard, coherent rock. The crystallization sequence of minerals in cooling magma is a topic that has been the subject of intensive study since the pioneering experimental work of Norman Levi Bowen, who conducted a series of meticulously controlled laboratory experiments at the Geophysical Laboratory of the Carnegie Institution of Washington in the early decades of the 20th century. Bowen's work, which was published in a series of papers beginning in 1912 and summarized in his landmark 1928 monograph, The Evolution of the Igneous Rocks, established the fundamental principles governing the order in which minerals crystallize from a cooling silicate melt, and these principles have come to be known collectively as Bowen's reaction series. Bowen's reaction series describes two parallel sequences of mineral crystallization, known as the discontinuous series and the continuous series, which proceed simultaneously as a melt of initially basaltic composition cools from its liquidus temperature. The discontinuous series describes the sequence of ferromagnesian minerals that crystallize from the melt, beginning with olivine at the highest temperatures, approximately 1,800 degrees Celsius for the pure magnesium end-member forsterite, followed by pyroxene, then amphibole, and finally biotite at lower temperatures. Each mineral in this series has a distinct crystal structure and chemical composition, and the transition from one mineral to the next involves a discontinuous change, or reaction, in which the earlier formed mineral reacts with the surrounding melt to produce the next mineral in the series. The continuous series, which proceeds in parallel with the discontinuous series, describes the progressive change in the composition of plagioclase feldspar as the melt cools. Plagioclase feldspar forms a continuous solid solution between the calcium-rich end member anorthite, which has the chemical formula called 2C2O8, and a melting point of approximately 1,553 degrees Celsius, and the sodium-rich end member albite, which has the chemical formula NaCl3O8, and a melting point of approximately 1,118 degrees Celsius. As the melt cools, the first plagioclase crystals to form are rich in calcium and poor in sodium, and as cooling continues, the composition of the plagioclase shifts progressively toward more sodium-rich compositions, a process that is described as continuous because it involves a gradual, progressive change rather than a series of discrete steps. At the lowest temperatures at the base of both series, the minerals quartz, potassium feldspar, and muscovite crystallize from the remaining melt, which by this stage has been greatly enriched in silica, sodium, potassium, and volatile components through the removal of the earlier crystallizing, higher temperature minerals. This progressive enrichment of the residual melt in silica and alkali elements through the process of fractional crystallization is one of the principal mechanisms by which the compositional diversity of igneous rocks is generated, and it explains, at least in part, the observation that the more silica-rich rock types, such as rhyolite and granite, tend to contain the mineral assemblages predicted by the low-temperature end of Bowen's reaction series. The examination of volcanic rocks in thin section under the polarizing microscope is one of the most fundamental and widely practiced techniques in igneous petrology, and it provides a wealth of information about the mineralogy, texture, and cooling history of the rock that cannot be obtained by any other means. A thin section is prepared by cutting a small slab of rock, typically measuring approximately 25 by 45 millimeters, and grinding it to a standard thickness of 30 micrometers, at which point most minerals become transparent and their optical properties can be examined using transmitted light. The thin section is mounted on a glass slide with an adhesive such as Canada balsam or epoxy resin, and a thin glass cover slip is placed over the specimen to protect it and provide a flat surface for examination. Under plain polarized light, the individual mineral grains in the thin section can be identified based on their color, pleochroism, which is the property of changing color as the microscope stage is rotated, relief, which is related to the refractive index of the mineral, and cleavage or crystal form. Under crossed polarizers, additional optical properties become visible, including birefringence, which is manifested as interference colors that depend on the mineral's optical properties and the orientation of the crystal relative to the polarizer and analyzer, extinction angle, which is the angle at which the crystal goes dark as the stage is rotated, and twinning, which is the intergrowth of two or more crystal domains that are related by a specific crystallographic symmetry operation. Plagioclase feldspar, for example, is readily identified in thin section by its characteristic polysynthetic twinning, which appears as a series of fine, Parallel lamellae that alternate between light and dark under crossed polarizers as a consequence of the repeated twinning on the Albite law. The composition of plagioclase can be estimated from the extinction angle of the twin lamellae, with calcium-rich compositions showing higher extinction angles than sodium-rich compositions. Olivine is recognized by its high relief, lack of cleavage, conchoidal fracture, and bright second or third-order interference colors, while pyroxene is identified by its two sets of cleavage intersecting at approximately 87 and 93 degrees, and its moderate birefringence. The geochemical classification of volcanic rocks represents a more rigorous and quantitative approach to rock classification than the simple silica-based scheme described earlier, and it relies on the precise determination of the concentrations of major, minor, and trace elements through analytical techniques such as X-ray fluorescence spectrometry, inductively coupled plasma mass spectrometry, and electron microprobe analysis. One of the most widely used geochemical classification schemes for volcanic rocks is the total alkali versus silica diagram, commonly abbreviated as the TAS diagram, which was formalized by Lobias and others in 1986 and subsequently adopted as the recommended chemical classification scheme by the International Union of Geological Sciences. The TAS diagram is a simple two-dimensional plot in which the horizontal axis represents the silica content of the rock, expressed as the weight percentage of SiO2, and the vertical axis represents the total alkali content, expressed as the sum of the weight percentages of sodium oxide, Na2O, and potassium oxide, K2O. The field of the diagram is divided into a series of named fields by a set of boundary lines, and a volcanic rock is classified by plotting its chemical composition on the diagram and identifying the field in which it falls. The principal fields include basalt, basaltic andesite, dacite, and rhyolite along the subalkaline series, and basanite, tephrite, phonotephrite, tephrophonolite, phonolite, trachybasalt, basaltic trachyandesite, trachyte, and trachydacite along the alkaline series. The boundary between the subalkaline and alkaline series is defined by a curved line that passes through the diagram, with rocks plotting above the line being classified as alkaline, and those plotting below it as subalkaline. The analysis of trace elements, which are elements present at concentrations of less than approximately 0.1% by weight in the rock, provides additional information about the petrogenesis of volcanic rocks that cannot be obtained from major element chemistry alone. Trace elements are particularly valuable because their behavior during partial melting and fractional crystallization is governed by their partition coefficients, which describe the tendency of each element to preferentially enter the solid or liquid phase during these processes. Elements with partition coefficients much less than 1, known as incompatible elements, are strongly concentrated in the melt phase during partial melting and are excluded from most crystallizing minerals during fractional crystallization, while elements with partition coefficients much greater than 1, known as compatible elements, are preferentially incorporated into the solid phase. The rare earth elements, which comprise the series of 15 elements from lanthanum, atomic number 57, to lutetium, atomic number 71, are a particularly useful group of trace elements for petrogenetic studies, as they behave in a coherent and predictable manner during magmatic processes. When the concentrations of the rare earth elements in a volcanic rock are normalized to their concentrations in a reference material, typically chondritic meteorites, which are believed to represent the primitive composition of the solar system, and plotted on a diagram with atomic number on the horizontal axis and normalized concentration on the vertical axis using a logarithmic scale, the resulting pattern, known as a rare earth element pattern or spider diagram, provides diagnostic information about the processes by which the rock was formed. For example, mid-ocean ridge basalts typically display relatively flat rare earth element patterns with a slight depletion of the light rare earth elements relative to the heavy rare earth elements, reflecting the depleted nature of their mantle source. Ocean island basalts, by contrast, typically display enriched patterns with elevated concentrations of the light rare earth elements relative to the heavy rare earth elements, reflecting the involvement of an enriched mantle source. Continental volcanic rocks often display more complex patterns that reflect the combined effects of partial melting, fractional crystallization, and crustal contamination. Isotopic signatures provide yet another powerful tool for investigating the origin and evolution of volcanic rocks, as the ratios of certain radiogenic isotopes are sensitive indicators of the source materials from which the magma was derived and the degree to which it has interacted with other materials during its ascent through the crust. The most commonly used isotopic systems in igneous petrology include the rubidium-strontium system, in which the ratio of strontium, 87 to strontium, 86 is measured, the samarium-neodymium system, in which the ratio of neodymium, 143 to neodymium, 144 is measured, and the uranium-thorium lead system, in which the ratios of lead 206, lead 207, and lead 208 to lead 204 are measured. The strontium isotope ratio of a volcanic rock is particularly useful for identifying the involvement of continental crustal material in the genesis of the magma as continental crust, which is old and has accumulated radiogenic strontium, 87 from the decay of rubidium, 87 over billions of years, has characteristically high strontium, 87 to strontium, 86 ratios, typically in the range of 0.710 to 0.730, while the depleted upper mantle, from which mid-ocean ridge basalts are derived, has much lower ratios, typically in the range of 0.702 to 0.704. A volcanic rock with a strontium isotope ratio that falls between these two ranges may indicate that the magma incorporated some proportion of crustal material through the process of assimilation, in which blocks of surrounding country rock are engulfed by the magma and partially or completely dissolved. The neodymium isotope system provides complementary information, as the depleted mantle has high neodymium, 143 to neodymium, 144 ratios, expressed as positive epsilon neodymium values, while continental crust has low ratios, expressed as negative epsilon neodymium values. The combined use of strontium and neodymium isotope ratios, often plotted together on a single diagram, allows petrologists to distinguish between magmas derived from different mantle source regions and to quantify the degree of crustal contamination that has occurred. The hafnium isotope system, based on the ratio of hafnium, 176 to hafnium, 177, has become increasingly important in recent years as advances in analytical technology, particularly the development of multi-collector inductively coupled plasma mass spectrometry, have made high-precision hafnium isotope measurements more accessible. The hafnium isotope system provides information that is broadly complementary to the neodymium system, but with some important differences in sensitivity to particular geological processes. And the combined use of neodymium and hafnium isotopes has proven to be a powerful tool for investigating the evolution of the mantle and the formation and recycling of continental crust over Earth's history. These isotopic measurements, while requiring sophisticated analytical instrumentation and careful sample preparation, have become an essential component of modern igneous petrology and are routinely reported in studies of volcanic rocks from all tectonic settings. The oxygen isotope system, based on the ratio of oxygen, 18 to oxygen, 16, provides yet another dimension of information about the origin and evolution of volcanic rocks. The mantle has a remarkably uniform oxygen isotope composition, with delta oxygen, 18 values typically falling in the narrow range of 5.0 to 5.8 per mil relative to the standard mean ocean water reference standard, and significant deviations from this range in a volcanic rock can indicate the involvement of materials with different oxygen isotope compositions, such as hydrothermally altered oceanic crust, which tends to have lower delta oxygen, 18 values due to exchange with seawater at high temperatures, or sedimentary rocks, which tend to have higher values. The measurement of oxygen isotopes in individual mineral grains and in volcanic glass, using techniques such as conventional fluorination mass spectrometry and secondary ion mass spectrometry, has become an increasingly important tool for unraveling the complex petrogenetic histories of volcanic rocks, particularly those from continental settings where the potential for interaction with isotopically diverse crustal materials is greatest. The application of electron microprobe analysis to the study of volcanic rocks has revolutionized the field of igneous petrology by enabling the precise determination of the chemical composition of individual mineral grains and zones within grains at a spatial resolution of approximately 1 to 5 micrometers. The electron microprobe works by focusing a beam of high-energy electrons, typically with an accelerating voltage of 15 to 20 kilovolts, onto a polished surface of the sample, and measuring the characteristic X-rays that are emitted by the atoms in the sample as a result of the electron bombardment. By comparing the intensities of these characteristic X-rays to those emitted by standards of known composition, the concentrations of individual elements within the analyzed volume can be determined with a precision of approximately 1 to 2% relative for major elements. This technique has been particularly valuable for the study of compositional zoning in phenocryst minerals, as the variation of chemical composition from the core to the rim of a crystal records changes in the physical and chemical conditions of the magma during the period of crystal growth, and this information can be used to reconstruct the thermal and compositional evolution of the magma chamber over time. Among the most celebrated and visually striking examples of volcanic rock formations found anywhere on the surface of the Earth, the Giant's Causeway, located on the northeastern coast of Northern Ireland in County Antrim, holds a position of particular prominence, and it has attracted the attention of scientists, artists, and tourists alike for several centuries. The Giant's Causeway consists of an estimated 40,000 interlocking columns of basalt, the majority of which are hexagonal in cross-section, although columns with 4, 5, 7, and 8 sides have also been documented, and these columns extend from the cliff face down to the sea, forming a series of stepping stone-like platforms that have an almost architectural quality. The columns were formed approximately 60 million years ago, during the Paleocene epoch, as a result of the cooling and contraction of a thick basalt lava flow, and the hexagonal pattern is a consequence of the physics of thermal contraction, in which the most efficient way to relieve the tensile stresses generated by uniform cooling is through the formation of a network of cracks that intersect at angles of approximately 120 degrees, producing hexagonal prisms. The process by which columnar jointing forms has been the subject of considerable scientific investigation, and it is now understood to be a consequence of the progressive cooling of the lava flow from the top and bottom surfaces inward. As the surface of the lava flow cools, it contracts, and the tensile stresses that develop as a result of this contraction are relieved by the formation of a network of fractures that propagate downward into the still cooling interior. The spacing of the columns is related to the rate of cooling, with more rapid cooling producing thinner columns and slower cooling producing thicker ones. At the Giant's Causeway, the columns typically have diameters ranging from approximately 30 to 50 centimeters, suggesting a moderate rate of cooling. Similar columnar basalt formations are found at many locations around the world, including the Devil's Postpile in California, Fingal's Cave on the Scottish island of Staffa, the Organ Pipes near Melbourne, Australia, and Svartafoss waterfall in Iceland. The Deccan Traps of Western India represent one of the largest volcanic provinces on Earth, covering an area of approximately 500,000 square kilometers and originally encompassing a volume of volcanic rock estimated at approximately 1.3 million cubic kilometers. Although erosion over the past 66 million years has reduced this considerably. The term traps is derived from the Swedish word trappa, meaning staircase, and it refers to the characteristic stepped topography that results from the differential erosion of successive lava flows of varying resistance. The Deccan Traps consist predominantly of tholeiitic basalt, erupted as a series of massive lava flows, some individual flows exceeding 10,000 cubic kilometers in volume, that were emplaced over a period of approximately 750,000 years, centered around 66 million years ago. Coinciding with the end of the Cretaceous period and the mass extinction event that eliminated approximately 76% of all species on Earth, including the non-avian dinosaurs. The precise role of the Deccan Traps volcanism in the end Cretaceous mass extinction remains a subject of active scientific debate, with some researchers arguing that the volcanic activity was the primary cause of the extinction, others maintaining that the Chicxulub asteroid impact was the principal agent, and still others proposing that the combination of both events, occurring in close temporal proximity, produced a synergistic effect that was more devastating than either event would have been in isolation. The volcanic gases released during the eruption of the Deccan Traps, including sulfur dioxide, carbon dioxide, and hydrogen fluoride, would have had significant effects on the global climate and atmospheric chemistry, potentially causing acid rain, ozone depletion, and both short-term cooling from sulfate aerosols and long-term warming from greenhouse gas accumulation. The Columbia River Basalt Group of the northwestern United States is another major continental flood basalt province, covering an area of approximately 210,000 square kilometers across parts of Washington, Oregon, and Idaho, with an estimated total volume of approximately 224,000 cubic kilometers. The basalts were erupted between approximately 17 and 6 million years ago, during the Miocene epoch, with the most voluminous phase of activity concentrated in a period of approximately 1.5 million years between 16.7 and 15.3 million years ago. The lava flows were erupted from a series of elongate fissures, some of which can be traced for distances of more than 100 kilometers, and individual flows traveled distances of up to 600 kilometers from their source, making them among the most extensive lava flows documented in the geological record. The most voluminous formation within the Columbia River Basalt Group is the Grande Ronde Basalt, which accounts for approximately 85% of the total volume and was erupted over a period of approximately 500,000 years between 16 and 15.5 million years ago. The average eruption rate during this period has been estimated at approximately 0.3 cubic kilometers per year, which, while modest compared to the estimated eruption rates for the largest historical eruptions, was sustained over a much longer period and resulted in the accumulation of an enormous volume of basalt. The flows of the Columbia River Basalt Group display a range of internal structures, including massive, vesicular, and columnar jointed zones, and they have been extensively studied as an analog for understanding the emplacement of flood basalts in general. The study of volcanic rocks is not confined to the Earth, as robotic spacecraft and, in the case of the Moon, Human explorers have returned samples and collected data that have revealed the volcanic histories of other bodies in the solar system. The Moon, which was visited by 12 human astronauts during the Apollo program between 1969 and 1972, is covered extensively by volcanic basalt, which fills the large, dark-colored areas known as Maria that are visible from the Earth with the unaided eye. The lunar Maria basalts were erupted between approximately 3.9 and 3.1 billion years ago, during a period of extensive volcanic activity that followed the late heavy bombardment, and they differ from terrestrial basalts in several significant respects, including their extremely low volatile content, the absence of hydrous minerals, the presence of unusual mineral phases such as armalcolite. Named after the 3 Apollo 11 astronauts Armstrong, Aldrin, and Collins, and their very high iron and titanium contents, with some lunar basalts containing more than 13% titanium dioxide by weight, compared to typical values of 1 to 3% for terrestrial basalts. The composition of the lunar basalts has been interpreted as reflecting the partial melting of the lunar mantle at depths of approximately 200 to 400 kilometers, under conditions of extremely low oxygen fugacity and in the virtual absence of water. The low viscosity of these iron and titanium-rich melts, combined with the lower gravity of the Moon, which is approximately 1/6 of the Earth's gravity, allowed the lava to flow over vast distances, filling the floors of large impact basins to depths of several hundred meters to several kilometers. The total volume of volcanic material in the lunar Maria has been estimated at approximately 10 million cubic kilometers, and while this is substantial, it is dwarfed by the volumes of volcanic rock produced on Earth. Mars, the 4th planet from the Sun, possesses an extensive volcanic history that is recorded in some of the most impressive volcanic landforms in the solar system. The Tharsis region of Mars is a vast volcanic plateau approximately 4,000 kilometers across and 7 to 10 kilometers above the surrounding terrain, and it is home to several enormous shield volcanoes, including Olympus Mons, which is the largest known volcano in the solar system, with a basal diameter of approximately 624 kilometers and a height of approximately 21.9 kilometers above the surrounding terrain. The volcanic rocks on Mars are primarily basaltic in composition, as determined by analyses conducted by the various lander and rover missions that have operated on the Martian surface, including the Viking landers in the 1970s, the Mars Pathfinder rover in 1997, the Spirit and Opportunity rovers beginning in 2004, and the Curiosity rover, which has been operating in Gale Crater since 2012. The Martian basalts are characterized by relatively high iron contents and low aluminum contents compared to typical terrestrial basalts, and they display a range of compositions that suggest derivation from a mantle source that has not undergone the same degree of differentiation as the Earth's mantle. The SNC meteorites, which are a group of meteorites believed to have originated on Mars based on their young crystallization ages and their trapped gas compositions, which match the Martian atmosphere as measured by the Viking landers. include both basaltic and more evolved compositions, and have provided important constraints on the volcanic history and internal composition of Mars. The most common SNC meteorites are the shergottites, which are basaltic to pocritic in composition and have crystallization ages ranging from approximately 175 million to 4.1 billion years, indicating that Mars has been volcanically active for most of its history, although the question of whether any active volcanism persists on Mars today remains unanswered. The economic uses of volcanic rocks are numerous and varied, reflecting the range of physical properties exhibited by the different volcanic rock types and textures. Basalt, owing to its hardness, durability, and resistance to weathering, is widely used as a construction material, particularly as crushed stone for use as aggregate in concrete and asphalt, as railroad ballast, and as riprap for the protection of shorelines and embankments against erosion. Approximately 16% of all crushed stone produced in the United States is basalt or similar dark-colored igneous rock, amounting to hundreds of millions of tons per year. Basalt is also used in the production of stone wool, also known as mineral wool or rock wool, which is a fibrous insulation material produced by melting basalt at temperatures of approximately 1,400 to 1,500 degrees Celsius, and then spinning the melt into thin fibers, much as cotton candy is produced from melted sugar. Stone wool is widely used for thermal and acoustic insulation in buildings and industrial applications, and it has the advantage of being non-combustible and resistant to moisture. Pumice, with its characteristic low density, high porosity, and abrasive texture, has been used for a wide variety of purposes throughout human history. In the modern era, pumice is used primarily as a lightweight aggregate in concrete, as an abrasive in cleaning products and personal care items, as a soil amendment in horticulture and agriculture, and as a filtration medium in water treatment. The global production of pumice and pumicite, the fine-grained equivalent of pumice, is estimated at approximately 25 million tons per year, with the principal producing countries including Turkey, Italy, Greece, Iran, Chile, and the United States. Pumice has also been used historically as a polishing and cleaning agent, and the ancient Romans were known to use pumice for smoothing the surfaces of parchment scrolls and for removing unwanted body hair, a practice that was widely adopted in the Roman bathing culture. Obsidian, as mentioned previously, has been valued for the manufacture of cutting tools and weapons since the earliest periods of human prehistory, and its use continues in certain specialized applications today. Obsidian blades, produced by the careful knapping of obsidian nodules, can achieve edges that are only a few nanometers in thickness, which is substantially thinner than the finest surgical steel scalpel. And there has been interest in the medical community in the potential use of obsidian blades for certain types of surgery, although this application remains largely experimental. In the decorative arts, obsidian has been used for the production of jewelry, ornamental objects, and mirrors since antiquity, with notable examples including the obsidian mirrors used by the Aztec and other Mesoamerican cultures for divination and religious purposes. Tuff and ignimbrite have been used extensively as building stone in many parts of the world, particularly in regions of active volcanism where these materials are readily available. The soft, easily worked nature of many tuff varieties makes them ideal for cutting and shaping into building blocks, and the resulting structures are lightweight, well-insulated, and resistant to fire. Notable examples of the use of volcanic tuff in architecture include the tufa buildings of Cappadocia in central Turkey, where entire cities, including underground complexes capable of sheltering thousands of people, were carved from thick deposits of Miocene-age tuff. The Moai statues of Easter Island, which were carved from the tuff of the Reno Raraco volcano, and the aforementioned colonial buildings of Arequipa, Peru, constructed from the locally abundant sillar, a white to pink ignimbrite that was erupted from nearby volcanoes. The relationship between volcanic rocks and agriculture is a topic of considerable practical importance, as volcanic soils, known by the technical term Andes soils, are among the most fertile soils found anywhere on the Earth's surface. The high fertility of volcanic soils is a consequence of several factors, including the relatively rapid weathering of volcanic glass and fine-grained minerals, which releases essential plant nutrients such as potassium, calcium, magnesium, and phosphorus into the soil at rates that are significantly higher than those observed in soils derived from most other rock types. Volcanic soils also tend to have excellent physical properties, including high porosity, good water retention, and a well-developed crumb structure that facilitates root growth and air circulation, and they commonly contain high concentrations of allophane, an amorphous aluminosilicate mineral that has an exceptionally high capacity for retaining nutrients and water. The distribution of volcanic soils closely follows the distribution of recent volcanic activity, and some of the most productive agricultural regions on Earth are located in areas with volcanic soils. The island of Java in Indonesia, for example, which has a population of approximately 150 million people concentrated in an area of approximately 129,000 square kilometers, making it the most densely populated major island on Earth, owes much of its agricultural productivity to the fertile volcanic soils derived from the numerous active volcanoes that dot the island. Similarly, the highly productive agricultural regions of Central America, the East African highlands, the Italian peninsula, and the Pacific Northwest of the United States all benefit from the presence of volcanic soils. The weathering of volcanic rocks, which is the process by which they are broken down and decomposed by the action of physical, chemical, and biological agents at the Earth's surface, proceeds at rates that are determined by the composition and texture of the rock, the climate, and the presence or absence of biological activity. In general, mafic volcanic rocks weather more rapidly than felsic volcanic rocks, owing to the greater susceptibility of the iron and magnesium-rich minerals to chemical weathering processes such as hydrolysis and oxidation. Volcanic glass, regardless of its composition, also weathers relatively rapidly compared to crystalline materials. because its disordered atomic structure is thermodynamically unstable and readily broken down by the action of water and dissolved acids. The weathering of volcanic rocks is an important component of the global carbon cycle, as the chemical weathering of silicate minerals consumes atmospheric carbon dioxide through a series of reactions that ultimately convert the CO2 into dissolved bicarbonate, which is transported by rivers to the ocean, where it is eventually precipitated as carbonate sediment. The role of volcanic rock weathering in regulating the Earth's climate over geological timescales has been the subject of considerable scientific attention, as it is believed to constitute one of the principal negative feedback mechanisms that has maintained the Earth's surface temperature within a habitable range over the past several billion years. According to the silicate weathering thermostat hypothesis, an increase in atmospheric CO2 concentration leads to an increase in global temperature, which in turn accelerates the rate of silicate weathering, which consumes CO2 and reduces its atmospheric concentration, thereby counteracting the initial temperature increase. Conversely, a decrease in CO2 concentration leads to cooling, which slows weathering and allows CO2 to accumulate from volcanic emissions, eventually warming the climate again. This feedback mechanism operates over timescales of hundreds of thousands to millions of years and is believed to have played a crucial role in preventing the Earth from falling into a permanent snowball or runaway greenhouse state. The study of volcanic rock types, as has been described at some length in the preceding discussion, encompasses a remarkably broad range of scientific disciplines, from the physics and chemistry of magma generation deep within the Earth's mantle, to the processes of eruption and deposition at the surface, to the long-term evolution of volcanic landscapes through weathering and erosion, and even to the investigation of volcanic activity on other planets in the solar system. The classification of volcanic rocks by their chemical composition, mineral assemblage, and texture provides a systematic framework for organizing this vast body of knowledge. And the relationships between these various properties reflect the fundamental physical and chemical principles that govern the behavior of silicate melts and their crystallization products. The practical significance of volcanic rocks extends far beyond the realm of academic geology, as these materials play important roles in construction, agriculture, manufacturing, and numerous other aspects of human activity, and the hazards associated with volcanic eruptions continue to pose significant risks to populations living in volcanically active regions around the world. The interaction between volcanic rocks and groundwater systems is another topic of considerable practical and scientific importance, as the permeability and porosity of volcanic rock formations play a crucial role in determining the flow and storage of groundwater in volcanically active regions. Basaltic lava flows, in particular, are often characterized by high permeability, owing to the presence of interconnected vesicles, cooling fractures, and lava tubes, and they can function as important aquifer systems capable of storing and transmitting large volumes of groundwater. The basaltic aquifers of the Hawaiian Islands, for example, supply the majority of the fresh water used by the approximately 1.4 million residents of the state, and similar basaltic aquifer systems are found in Iceland. The Columbia Plateau of the northwestern United States, and many other volcanic regions around the world. The chemistry of groundwater that has interacted with volcanic rocks is typically characterized by elevated concentrations of dissolved silica, calcium, magnesium, sodium, and bicarbonate, reflecting the dissolution of volcanic minerals and glass, and the temperature of the groundwater may be elevated in areas where residual volcanic heat provides a geothermal energy source. The aesthetic qualities of volcanic rocks have also been appreciated by human cultures throughout history, and various volcanic rock types have been used as decorative and ornamental materials in architecture, sculpture, and the decorative arts. Obsidian, with its deep black color and brilliant vitreous luster, has been polished and shaped into jewelry, mirrors, and ornamental objects for thousands of years, as has been previously noted. Basalt, particularly the fine-grained varieties with uniform color and texture, has been used for sculpture and monumental construction in cultures ranging from ancient Egypt, where basalt was used for sarcophagi and statuary, to modern landscape architecture, where basalt columns and boulders are used as decorative elements. The so-called bluestone of Stonehenge, which forms the inner circle and horseshoe of that famous Neolithic monument in southern England, has been identified as a variety of volcanic and metamorphic rock originating from the Preseli Hills of southwestern Wales, approximately 240 kilometers from the site. And the transportation of these massive stones over such a distance in the 3rd millennium before the Common Era remains one of the most discussed topics in British archaeology. The total volume of volcanic rock that has been erupted at the Earth's surface over the course of geological time is difficult to estimate with precision, but it is certain to be enormous. As volcanic activity has been a continuous process throughout the Earth's 4.56 billion year history. The present-day rate of volcanic rock production has been estimated at approximately 4 to 5 cubic kilometers per year, with the majority of this production occurring at mid-ocean ridges, where the creation of new oceanic crust by basaltic volcanism is a fundamental component of the plate tectonic cycle. The total volume of oceanic crust currently present on the Earth's surface is approximately 2.5 billion cubic kilometers, and this entire volume has been produced by basaltic volcanism and subsequently modified by metamorphism and alteration over the past approximately 200 million years, as no oceanic crust older than this is preserved on the modern ocean floor. The continental crust, which is composed of a more diverse assemblage of rock types, but includes significant volumes of volcanic rock, has an estimated total volume of approximately 7.2 billion cubic kilometers and has been accumulating over the past 4 billion years or more. The volcanic rocks within the continental crust span the full range of compositions from basalt to rhyolite and include some of the most voluminous volcanic deposits known. such as the continental flood basalt provinces described earlier and the vast ignimbrite sheets associated with major caldera-forming eruptions. The preservation of these volcanic rocks in the geological record and their subsequent exposure at the surface through uplift and erosion provides geologists with an archive of the Earth's volcanic history that extends back to the earliest periods of the planet's existence. And the study of this archive continues to yield new insights into the processes that have shaped the Earth and the other terrestrial planets over billions of years of geological time. It is through the patient and methodical examination of volcanic rocks, their compositions, textures, mineral assemblages, and isotopic signatures that the story of the Earth's internal dynamics is gradually being deciphered, one thin section, one chemical analysis, and one isotope ratio at a time. The volcanic rocks that are found scattered across the continents and that form the floor of every ocean basin are not merely inert geological curiosities, but are, in a very real sense, messages from the deep interior of the planet, each one preserving a fragment of information about the conditions that prevailed at the time and place of its formation. The study of these materials, which has occupied the efforts of countless geologists, geochemists, and geophysicists over the past 2 centuries, continues to be a vibrant and productive field of scientific inquiry. And it is likely to remain so for many decades to come, as new analytical techniques, new theoretical frameworks, and new observations from both terrestrial and planetary exploration continue to expand our understanding of the processes by which volcanic rocks are generated, erupted, and deposited on the surfaces of the Earth and the other rocky planets of the solar system.